again, we really only have 3 lessons in this unit. And they're what the inverse variation, or the variation stuff, doesn't really have anything to do with this stuff here. But that's why we're just calling it a miscellaneous unit, and we're putting all that together. All right, this one is, we're talking about systems of equations. These are the requirements, according to the SOLs, what we're supposed to be studying. Okay. Supposedly, you learned about systems of equations in Algebra 1. And there, everything you did was linear. In Algebra 2, we're supposed to be dealing with nonlinear systems of equations. And it's actually only covered on 1 page in the middle of Chapter 10. I think it's page 661. That is all there is to it. And that's all we have really to go off of. We understand that most probably don't remember so much about systems of equations. So today's lesson is really not addressing these yet, but it's getting us ready to address these in the next lesson. Okay. So systems of equations, or a system of equations. A system of equations means more than one. Generally, you have as many variables as you have equations. So you could have 2 equations and 2 variables, 3 equations and 3 variables, 4 equations and 4 variables, and so on. Right? The equations we use to model the atmosphere is 7 equations and 7 variables. We will only be dealing with 2 equations and 2 variables. It's not that you can't have more variables than equations, but you won't be able to solve it unless you've got the same number of equations as you have variables. Okay, so yeah, you could have an equation that's got many variables in it. All that means is you can't solve for any particular one, at least not explicitly. You could solve in terms of the other variables, but we're generally dealing with systems where, because we have the same number of equations as we have variables, we should be able to solve them. That's a good question, good point. So by linear systems, what we mean is both of our equations are linear. And what does it mean when an equation is linear? The graph is a straight line, and the equation itself, both the x and the y have exponents of 1. Right? It's when they get exponents that are more than 1 that you get quadratics and cubics and things like that. But in our problem here, the x's and the y's will have an exponent of 1, which means you don't see it. Okay. It's nonlinear if one of those equations is nonlinear. So we're supposed to be dealing with either a linear quadratic, meaning one will be a straight line, the other one will be a quadratic, or it could be a quadratic. Both could be quadratics. Okay, the solution to a system are the set of points that would satisfy every equation. If it's just 2 equations, then it would be the points that satisfy both equations. In terms of the graph, it's where do the graphs intersect. That's the solution. Right? Just look for where the two graphs intersect. Those are the answers. My experience, limited as it is, because we've only been dealing with our new SOL for the last couple of years, is that there'll probably be a couple, no more than 3, but probably like 2 questions about systems. And one of them will be a graph of more than one graph on the same background. It'll say, what are the solutions? Or how many solutions do you see? Something like that. So it's basically just testing whether you understand that one concept. So when you're dealing with a system of linear equations, those 2 lines in the same plane, if their slopes are different, then those are going to cross in one spot, one point. That one has one solution. If their slopes are the same, then you have one of 2 possible situations. Either they're parallel, means they never touch, which means there's no solution, or they're actually right on top, one right on top of the other, which means every point that's on one line is on the other line, which means there's infinitely many solutions. So I wouldn't get worked up about these things that are underneath, but that's what consistent and independent means there's one solution. Okay, consistent but dependent means it's the same line, and if it's inconsistent, there's no solution. Okay, so if it's a linear and a quadratic, then here's your possibilities for solutions, right? How many different intersection points could you have if you were going to have a straight line and one of these 4 shapes? Well, I should back up for a second. Up till now, when we dealt with quadratics, we were dealing with quadratic functions which we knew have a shape of a parabola. This one page in chapter 10, that's a chapter about quadratic equations that are not necessarily functions. In fact, they could be circles, they could be ellipses, or they could be hyperbolas. And a hyperbola is actually a shape that you know. If you remember the graph of an inverse variation where we would sketch one piece in quadrant 1 and one in quadrant 3, that's a hyperbola, right? They're called the conic sections. And we don't do much with that in Algebra 2. We do a lot with that in pre-calculus. But just how many points, what would be the most points that you could, of intersection, you could have between a straight line and an ellipse like this? 2, right? You could have 2 points of intersections. There's one solution and there's another. Is there any way you could have just one solution? Okay, Carrie, if you go like that, right? So there would be one solution. Could you have no solutions? Sure. There's a no solution. The same thing could be true over here, right? There's a 2, there's a 1, and there's a none. And even a hyperbola. How could you have here, I mean, hyperbolas, there's your 2. How could you have 1? Say again? Yeah, I mean, you'd have to put it right through the middle of these 2, right? Like this. Like that. So it's just touching one branch of the hyperbola. So there would be your 1. And then if you made it even more to the right there, then there's a none. That would be a none. Yep. Okay, well, what about how many different ways? Just trying to picture these shapes here. What if you had 2 of these shapes on the same background? How many different points of intersection could you get by having an ellipse and a circle on the same background? What would be the most number of points of intersection? Okay, so if you looked at that, if you had an ellipse and a circle, how many points of intersection? 1, 2, 3, 4. And you could play with these shapes, but there's no way you're going to have more than 4 for any of them. Is there any way you could see, we're just playing with these 2 shapes, is there any way you could have 3 points of intersection? Yeah, if you move this circle, that's not a very good circle, but if you move that circle up, it could still have those two and then just touch the bottom with one, right? Something like this. Make sure that touches. Right? Is there any way to have just two? Yeah, if you move it up even more, and then again, yeah, you could have just one or you could have none. There's a one. The main thing to understand is when you're looking, when it says what is the solution, if it's a system, then you're looking for the points of intersection. I mean, we know when we're dealing with parabolas or polynomials that when it says what's the solution in a graph, you're looking for the x-intercepts, right? But not with this. Sometimes these shapes are on a background and you might be looking at the x-intercepts like they're solutions, but they're not because it's a system. So we have three ways to solve the systems of equations: substitution, elimination, and graphing. And by graphing, it's actually the same concept that we've already talked about. You know, you look for the points of intersection. Well, what we really hope to do here is to put it in the calculator. I can tell you that fifth block today, that was my intent, but we didn't get to it. So we'll just do it next class, which is fine. But we will for sure be able to get through these two today. Right? Substitution, elimination, and those are the two methods you should have seen before. Whether you remember the names or not, I bet that when you see them, you'll go, yeah, I remember how you do that. So substitution. Right? The steps to solve a system by substitution, a system, a 2x2 system, right? Two equations, two variables. First step, you solve one of the two equations for one of the variables, and you can choose which one. There's no wrong variable to solve for here. Although there's sometimes a kind of obvious one you should be choosing. If you choose a different one, you can still be right. So we solve one of the equations for one variable. We substitute for that variable in the other equation. When you did that, now there's only one equation and one variable, and that's something you can solve with some pretty basic algebra. But remember, our solution is going to be the value of two variables, right? It's not going to be just the one that we solve in step 3. Once we know the x or the y, we got to plug it back in somewhere to find the other. And where do we plug it back in? That equation you solved in step 1 will be the perfect place to substitute that answer to get that answer. Alrighty. So here is a system What does the first step tell us to do? Solve one equation for one variable. Now, like I say, you could solve for either variable in either equation, but there really is an obvious choice here. You tell me. The second one for y. Why? Because it's easier? What makes it easier? Yeah, there's a coefficient of 1 there, which means, you know, you don't have at the last step, you're not going to have to divide by a number. And if you did, like here, if I solved this one for x, at the last step I would have to divide by 3, and that would make fractions. And then I'm plugging in fractions into the other equation. That's not easy, right? Or it's not as easy as plugging in for y, because there's the 1y. So like I say, you could pick any one you want, but there is a recommended choice here, and that would be solve the second one for y. Okay, what would that look like? Y equals 10 minus 2x. Subtract 2x from both sides. Okay, that's step 1. What is step 2? Okay, so this one here became that. So now we want to plug this in here. That's going to be step 2. So 3x plus 4 times 10 minus 2x equals 12. So you could see that is this equation. It's just I've replaced the y with 10 minus 2x. See, that should look like it's the same thing. Okay. Now what we've got there is one equation and one variable that can be solved with some basic algebra stuff, right? Distribute. Combine like terms. Subtract 40. What is that going to be? Negative 28. Divide by negative 5. Okay, there's the x coordinate. How do I find the y coordinate? Yeah, I'm going to go back to the result of step 1 was to make this equation. And because it's already solved for y, that's the perfect place to plug in for x and find y. Right, so this goes in here. Y equals 10 minus 2 times 28 over 5. Y equals 50 over 5 minus 56 over 5. Where did I get the 50 over 5 from? That's 10, right? And why did I do that? Because the other term has got a denominator of 5. I need it to all be fifths. Okay, now what is 50 over 5 minus 56 over 5? Minus 6 fifths. Okay, so the solution is 28 fifths, negative 6 fifths. Do you remember doing this somewhere in the past? So try that one. Try to do the same thing with that one. So which equation are you solving for which variable? Yeah. Probably the first one for x would make it the easiest possible problem. Okay. You do it? Let's switch. That's 1 plus 6y minus 10 minus 4y. 2y. If you add 10 to both sides, you don't get negative 15. This is on one side of the equation. That's on the other.
Yeah, it's fine.
What does that say? Negative 9?
It's fine.
Okay. I'm not sure. You need to switch those because you said x is negative 5 halves. That's the first. Other than that, it's right. Huh?
When we're going back to solve second variable, first one, do we plug both?
No. Where did you? Okay, there's there. I did, and you solved for y and you got 5 halves. So now you go up here and put in 5 halves.
For this one.
Yes. Remember, it's the result of the first step. That's the result of the first step. That is the x, and what is the y? And, okay, that's correct. You got some right answers. Your y is correct, but your x is not. You are wrong and wrong. Lee. That is right. Yes and yes. Everybody got that right? Plug in. Negative 2 times 5 minus 3y minus 4y equals negative 5. So now we have one equation, one variable, solve. Negative 10 plus 6y minus 4y is negative 5. Combine like terms. Negative 10 plus 2y is negative 5. Add 10. 2y equals 5. Y equals 5 halves. Now, if you did this part right, let's say you solved that right and you plugged in there and everything was right up to there, and you made some mistakes after that, it's still, something significant that you did understand what you're supposed to do. Show the work. And then what do I do with that 5 halves? Yeah, remember the result from step 1 is the perfect place to find the other variable. So we say x equals 5 minus 3 times 5 halves. X equals 10 halves minus 15 halves. X equals negative 5 halves. So that is a point, right? Negative 5 halves, 5 halves. Which quadrant do these two lines cross? The x is negative and the y is positive. Second quadrant. You'd be looking for the intersection point. Okay. Now, elimination, first you could see I got 5 steps here, but the first one is blank. I'll put that one in later. Before you do elimination, both the equations should be in standard form with the variables lined up. By standard form for straight lines, remember that is ax plus by equals c. It should be there's an x term and plus a y term on the left and a constant term on the right. That's what we mean by standard form. And really, both of the systems we already did, they were in standard form, right? They were standard form, ax plus by equals c. Ax plus by equals c. The x's are lined up, the y's are lined up, the constants are lined up, the equal signs are lined up, right? That's what we mean. You definitely want it looking like that before you try to solve. So here is a system. It's in both of them are in both equations are in standard form. The x's are lined up over the y's are lined up, and the constants are lined up, and the equal signs are lined up, right? So we skip over the first step. The second step would tell us to do what? Yeah, add them to each other, right? Add up the x's, add up the y's, add up the constants. Okay, well, what do you got when you add up 4x plus negative 4x? They eliminate each other, right? That's why it's called elimination, because in this step, you will eliminate a variable. Okay, now, so this is 0. 2y plus 3y is 5y. 9 plus 16 is 25. All right, now we've got one equation and one variable solved. Y equals 5. Now, how do we find the x? Okay, but here's the part where you have to choose now. You don't have an obvious place to go like you do with substitution. Right? Here, you're just going to pick which one of those equations do you want to plug it into. Sometimes it'll be obvious, maybe the one looks a little easier to deal with. I'm not sure that this is really that much true. Anybody have a preference? Curtis? Yeah, I think that would tip my choice towards the first one because it's positive 4x and not negative 4x. I would probably plug in there. So go up here and plug in 4x plus 2y. Oh, that was wrong. Plus 2 times 5 equals 9. 4x plus 10 equals 9. 4x equals negative 1. X equals negative 1/4. So there's your point, right? Negative 1/4, 5. Do you remember doing this one? Half and half? We used to have this whole chapter. Chapter 3 used to be part of what we did, and then a few years ago they cut it out. My suspicion is that Algebra 1 teachers do not spend much time on this, if at all. So go ahead and try to do the same thing with this one. Add them up. Yeah. What'd you get? Yes. They got one correct. Correct. So what'd you do to your hands? Was it last Monday? Oh, okay. Does it hurt? Is it broken? Couldn't tell with an X-ray. Incorrect. How did that end up being negative 12? Negative 8 plus. Who got answers? Correct. Where's yours? Correct. Correct. So what was the answers? 4, 0. Right, so because the 8y and negative 8y are opposites, you can add them up and cancel the y's, right? You wouldn't take this step if that wasn't true. So this is 3x equals 12, x equals 4. Okay, now where are you going to plug that in to find the other? The second one? It doesn't matter, right? So, especially because we know what the answer is. So this one will go 5 times 4 minus 8y equals 20. 20 minus 8y equals 20. Negative 8y equals 0. Y equals 0. So there's your point. 4, 0. Which quadrant is that in? Where is it? It's on the x-axis, right? Because the y is 0. It's not actually in a quadrant. It's along the x-axis. Trick question. Okay, now the thing is, it's not often that you already have one of the variables where they have opposite numbers for coefficients, so that when you add them up, they're going to eliminate a variable. Usually you got to do something to make that happen. And in this problem here, right, these aren't going to cancel, these aren't going to cancel. You have to choose to multiply each equation by a constant so that you create a situation where they have opposite coefficients. And, you know, again, you could choose different things. And they obviously chose to multiply the first one by 3 and the second one by -2. They could have done -3 and +2. They could have done +2 to make that a 14y and they could have said +5 to make that a 35y and a -7 to make that a -35y, right? So you have options here. But they clearly, to go from here to here, they multiplied this one by 2 and this one by -3. That's the missing first step. And you don't always have to do it, right? Sometimes it won't be necessary. Do you have a question? Okay. Oh, you're right. Thank you. Okay. 3 and -2. Okay, when you do that, this system of equations is called an equivalent system. I mean, it'll cross at the same point as this one will. So we can solve this one and get the answer that we're looking for. Those are called equivalent systems. So the missing step 1 is not always necessary, but if it is necessary, then you're going to have to, it's kind of like finding a common denominator to figure out how you're going to make these numbers cancel. Now, once you've got it at that point, now it's going to be like solving one of the others, right? Add them up. 11y equals 22, y equals 2. Now, here's where it's a little bit different. Remember, you go on number 4, it says substitute that answer into one of the original equations and you choose. Well, what do you mean by the original equations now? Do we mean these or do we mean these? And it doesn't matter. Pick whichever ones you want. Any one of the 4 will solve this for you. You know, these are probably smaller numbers because it was before you multiplied by a constant. But you could use these equations too. How about if we do that since it's on the same page? How about I'll pick the first one. 6x plus 21 times 2 equals 12. 6x plus 42 equals 12. Okay, subtract 42. 6x equals -30. X equals -5. So again, when you get to this step here, you can choose one of these two, or you can choose one of the equations before you multiply. You get the same answer in any case. Well, hopefully you do. So you try to do the same thing there. You're going to have to do the step 1. Figure out what do you want to multiply each equation by so that one of the variables have opposite coefficients. You do what? You have to, yeah, whatever you choose to multiply by, you're going to have to multiply all three terms by it, the left and the right, every term. Well, I mean, if you're going to keep your numbers as integers and not fractions, you're going to have to multiply both of these by something, right? I mean, some students would say, I'm going to multiply the first one by -5/3. And yes, that would give you a -5x there. But now you created all other kinds of fractions. But some will do it. Do what now? Okay, well, if you multiply this one by -1, let's say, then you got -3x, -7y, -15. You still, neither one of these are going to cancel if you add them up. They have to have exactly opposite numbers for coefficients so that when you add them up, they cancel. It's not enough just to be opposite signs. They have to be opposite numbers. Did you do it? What does that say right there? Is that a 7? Then why are you multiplying times 7? Don't you mean to multiply that one by 2 and that by 7? Okay. Let's see. Okay, so you multiply by 5 and -3. 15 plus 35 equals 75. -15 minus 6y equals +12. You add them up, you got 3. And then you substitute back up here. You got, isn't 6 divided by 3 -2? Yeah. Almost. Close, but no cigar, as they say. Yes. Got 2 answers. What about Josh? You mean not yet?
What are these called?
This is elimination.
What exactly didn't have another name?
Well, it's solving systems, linear systems of equations and elimination. That's, we're solving systems and we're solving them with elimination. So how many eliminated the x's as your first? How many did the y's? Okay. You know, there's really not one that makes it obvious, you know, which one to do. I mean, sometimes there is. You know, what if this one said 6x plus 2y equals -4? And then you would only have to multiply one equation by something to eliminate x's and 2 to eliminate y. So it'd probably be, okay, choose the x's. But it doesn't really matter in the end. You could do any one you want. So let's do the x's. So what did you multiply the first one by? +5? Okay. Did anybody go -5? Nobody. Oh my gosh. Okay. So multiply. Remember, we multiply everything. So that's 15x plus 35y equals 75. -15x minus 6y equals 12. X's are eliminated. 35y minus 6y. Right? Luckily, 29 goes into 87 3 times. Okay, and then where are you going to plug into to find the second variable? You know, probably one of these here. It's on the same side. It's easy. The bottom one. So you say 5x plus 2 times 3 equals -4. 5x plus 6 equals -4. 5x equals negative 10, x equals negative 2. So the answer is negative 2, 3. All right, now there's two special cases here. And these are already worked out to a point. Notice in this first one that the coefficients are opposite, actually on both variables. So what happens when I add the two equations together? Yeah, the x's and the y's are eliminated in the same step. And now on the right-hand side, negative 5 plus 5 is 0. We end up with an equation which does not have a variable in it, which means the solution that does not depend on the variables. It's either always true or it's always false. And if 0 equals 0 is a true statement, then it's always true. Is 0 equals 0 a true statement? Yeah. So this one is always true, meaning the two lines are right on top of each other. That's what it means when you eliminate the variables and you end up with a true statement. True. Right? So same line, infinite solutions. Sometimes the way it'll be stated, it'll say no unique solution. It's a unique solution if it's just one point, right? That if it's infinitely many points that make up those lines, then it's not a unique solution, right? In this one, same deal on the left. And we add these two together, the x's and the y's cancel. But on the right, we got 16. So we have a statement which is 0 equals 16. So the answer does not depend on the variables because there are no variables. Is that a true or a false statement? It's false. It means no solution. So what do those two lines look like on the graph? They're parallel. They never cross. There are no points in common. So when you add them up and you end up with this, you say that's false. So that is parallel lines no solution. Okay. So these two, one of them is no solution. One of them is infinitely many solutions. Which one is which? No, you probably could see just by looking at it, right? You say which one is true, which one is all no solution, which one is infinitely many solutions. Just imagine on both of these, you're going to have to multiply by something, right? You're going to have to take that first step before you can get there. What are you going to multiply by? Which equation here? By 2, right? You're definitely going to go the first one by 2. And I'm going to do something which generally, if I was doing this for myself, this is what I would do. I'm not going to rewrite the second line. I'm just going to leave it, the second equation, just leave it there. And now this equation, when I multiply times 2, is negative 2x plus 2y equals negative 4. And so now here's just looking at the second and third, that's my system. Okay, what's going to happen when I add them up? Am I going to get a true statement or a false statement? It's going to be false, right? It's going to be 0 equals negative 4. So no solution. How about the second one? What are you going to get? Is it going to be a 0 equals 0? What are you going to multiply by the first equation? Negative 3? You know, if we're going to do it like we're doing, we'll call that negative 3, which gives, then I'm going to put that result right underneath. Negative 12x minus 3y equals negative 18. And they're opposites. All three are opposites, so they get total cancellation. which means it's always true. It's the same line, infinitely many. Same line, infinite solutions. Now, I have to say, and I'll say this because some of you in here would probably benefit from this, but let's say that I'm dealing with, I'm going to make it up. Insert page. If you add those up, is it going to eliminate the x's? What if you subtracted one from the other? Yeah, I mean, in effect, subtracting one from the other is the same thing as multiplying everything by a -1 and then adding them. And honestly, I would not take the step of multiplying by -1. I would just say, I'm going to subtract that equation minus that equation. 2x minus 2x cancels. 5y minus 3y is 2y. 20 minus 8 is 12. Y equals 6. So, you know, if you've already got them, they're exact. They're not opposites, they're exact. Then subtracting is the same thing. You may not want to take that step of actually multiplying by -1. Okay, now I had prepared to do the solve by graphing, and that's not going to happen because this took too long. We'll do it next time. So that means we can't do this, but we can do the others. These are all the solving like we just did. Substitution, elimination. Now I'm going to come around and sign off on the U-tries and tell you the grade on the test and that, because we just don't have that much time, but you will know. So you can start making plans if you're going to retest.